All right, 6:05, guys. We're going to start now. All right, so this is our sixth OCI session, and today we're going to be covering reactions and mechanisms. And I'm pretty sure this is very vital for organic chemistry because when we think of organic chemistry, we're thinking about reactions and mechanisms, generally speaking. The stuff you guys have done so far, it's sort of niche topics like Newman's and chair projections. You really won't ever use them going forward. Sometimes you do, but you rarely use them. When we talk about organic chemistry, it's all about reactions and mechanism from now on, and then for the entirety of organic chemistry too as well. Okay, so good on you guys for showing up. Oh yeah, attendance. Please scan this QR code.
You're unmuted, right?
No, I'm muted.
You're muted or they're
Unmuted. I'm unmuted.
You're unmuted?
Yeah, because I need to record the voice.
Yeah. I was making sure.
All right, give me a thumbs up if once you guys have filled it out. All right, I think everyone has gotten it now. Okay. So today, our session can be split into 5 subtopics: 1, enthalpy; 2, kinetics; 3, nucleophiles and electrophiles; 4, carbocations and rearrangements; and then the last one is mechanisms. These last 3 bullet points are probably going to be the most important, the focal point of this OCI session. So yeah, without further ado, let's get started. First topic is about enthalpy. So enthalpy, it's denoted as delta H, and it measures the amount of heat, right? And this is very important because when we do reactions and mechanisms, reactions are basically the breakage and the formation of bonds, right? And to do that, we need energy. And this energy comes as a form of heat. So we use delta H to represent that, okay? And when we break these bonds, energy is released, right? We need to put in energy, and energy is released. And this energy is called bond dissociation energy. So if we see this example on the bottom, we see that this XY molecule is being broken apart, and that requires energy. So delta H will be put in. Okay, moving on. And some of these bond dissociation energies are quantified using kilojoules per moles. You don't have to memorize these values at all. If Jesky does ask you problems based on bond dissociation energy, he'll give you this table and these values. So don't worry about it.
You should take a picture of this for the practice problems.
That's true. I think they're on next slide. Oh yeah, they are. These are on the next slide. You don't have to take a picture, guys.
Sorry, you can yell out.
So these type of enthalpy problems with involving bond dissociation energy, I can't guarantee it, but Jesky will most likely not ask these type of problems, asking you to calculate delta H. But I know he includes these in his PowerPoint slides that he does. And when Alexi and I took it, he never asked these type of problems, but it may be different this semester. So we'll go over it just in case. So when we do these type of problems, how we calculate delta H and constant pressure is we look at the amount of bonds broken and then subtract that energy with the bonds formed. So to do that, we just look at this reaction. We see that here, that this molecule is converted into this molecule, right? And to do so, we need to break this bromine bond with the carbon. We have to cleave it. But at the same time, we're going to also form a new bond between this carbon and this OH. So, and the same case here with water and HBr. The hydrogen bond is going to be broken and then form a bond with a bromine. So all we got to do now is add up all the energy for broken bonds. And we see that this carbon here and this bromine here, it breaks. And if we see on the table on the right, we look for that exact one, which is right here. I'll circle it in red. And we see that under kilojoules per moles, we get 272 kilojoules per moles. So we're going to add that value for bonds broken. That's one of them. There's also another one that's broken. H2O, the hydrogen is broken off the oxygen. And we can see that over here. I circled it. And this value is 498. Cool. Okay, so now that we've identified all the bonds that are broken, we're going to identify the bonds that are formed now. And we see that there's a new bond between this carbon here and this OH group. And we can see that on, where is it? Okay, yeah, it's right here. And we see that the energy is 381 kilojoules per moles. And then another bond is formed between hydrogen and bromine. So we see that right here, 368 kilojoules per moles. Now that we got all the okay, sorry. Now that we got all the values to calculate delta H, we add all the bonds broken, the energies on bonds broken, which is 272 plus 498. And then subtract that with the bonds formed, 381 kilojoules per moles plus 368. And then if we punch this into the calculator, you'll get positive 21 kilojoules per moles. And that's the amount of heat you would have to put in for this reaction to occur. Does my thought process make sense? Okay. So yeah, that's how you solve these type of problems.
The heat, put it into the heat release.
Um, since this is positive, it's endothermic, so you have to put in heat pressure. So here's our answer key. You get the same results. All right, and this stems into the next topic of exothermic versus endothermic. Reactions involve the formation and breaking of multiple bonds, and the total change in enthalpy is these energies all combined together. And to put it simply, if your delta H is a negative value, that means it's going to be an exothermic reaction, meaning it's going to release heat. If it's an endothermic reaction, your delta H is going to be positive. So you're going to have to put in a lot of energy. All right. And we can see this in the graph here, this energy diagram. This delta H here is a negative value. And this delta H here is a positive value. All right, so pretty simple question here. Can one of you guys tell me whether this energy diagram is exothermic or endothermic? Yup, pretty simple stuff. Endothermic because our delta H is positive.
Is C or D the delta H?
That's a good question.
D, yes.
Yep, this is delta H. Do you know what C is then? Yep, you already know your stuff. Okay, that's the key. And then enthalpy can also be related to Gibbs free energy. Gibbs free energy, when we talk about Gibbs free energy, we're talking about the spontaneity of a reaction and how likely the reaction is to proceed and if it's going to completion towards the products or not. So likewise with enthalpy, we use delta G to determine if a reaction is exergonic or endergonic. And it's going to follow the same principles in the fact that if it's a negative delta G, it's going to be an exergonic reaction. If it's a positive, then it's going to be an endergonic reaction. What the? This is bugging. Sorry about that. So yeah, same trend with enthalpy as with Gibbs free energy. Okay. Any questions? Okay. So that covered the entirety of enthalpy for what you need to know. We're going to move on to kinetics next. And kinetics essentially is the study of rate and how fast a reaction can occur. And to represent this in a form of an equation, we got this rate equation where rate equals the K constant, which is also known as a rate constant, multiplied by the concentration of your starting materials or reactants. Okay. And if you notice, the bigger the K value is, the faster the rate is going to be. All right. Yeah. So if we look at the rate, it's directly proportional to the K value here, right? The rate constant. So naturally, if the K value is increases and it's larger, that means the rate is also going to increase. Does that make sense?
So like if K doubles, the rate will double.
Yep. Kinetics. So to increase or decrease the rate of a reaction, it all depends on three factors here. And these three factors include temperature. So if you think about it, if you have like a reaction chamber, let's say, with many different types of molecules, temperature is going to affect the rate of this because if we increase the temperature, that means we're also increasing the kinetic energy of each molecule. And if we increase the kinetic energy, that means each molecule is traveling a lot faster, which also then means that these molecules can collide more frequently, which means it's going to increase the rate. So temperature is one of them. Next one is we got energy of activation or activation energy. And it's saying that the lower your activation energy, the faster your reaction proceeds. And this is pretty self-explanatory because if we look at this graph on the right here, lower activation energy means lower energy you have to put in for the reaction to proceed to the products. So that's the second one. And then the last one is sterics. Sterics has to do with the geometry and orientation of the molecules. And we know that for a reaction to proceed, the molecules have to collide at the very right orientation and geometry so that products can be formed. So you need the proper sterics as well for a reaction to occur. Do those three factors make sense?
Wait, what was sterics again?
Sterics is basically has to do with the geometry of the molecules. So if you want a reaction to proceed and make product, the reactants have to collide at just the right angle and just the right orientation so that the collision can make the products. If it's in an improper orientation, it won't make any products, essentially.
So like if it's like, say we just have like this molecule, and if we wanted to like replace this chlorine with something, it would have to go from this way. It can't attack it from like that way or like that way. It would have to go from this way. So that's what sterics basically is.
Yeah, I mean, also, if you remember when drawing chair conformations, you guys talked about steric hindrance, right? Steric hindrance is basically the orientation of those substituent groups and how they contribute to the stability of the chair conformations, right? Oh. Likewise, the sterics here is the same thing. They have to be in the proper orientation for them to collide. Because if it's too bulky, then they can't collide at the same time, right? Make sense? All right. All right, so let's do a practice problem here. If I wanted the following reaction to proceed faster by increasing the rate constant K, which of the following should I do? So this is directly correlating back to our previous slide talking about the three main factors that change the rate constant. So I'll give you guys a minute to look through these answer choices and then we'll come back. I think majority of you guys have the answer now. Does anyone want to take a guess what it is? You said D? Yep. D is the correct answer. Do you mind explaining why?
I just remember.
another class, but that's the only one. That's all I know.
Yeah. So, first off, let's try to do process of elimination and explain why the rest of the four answer choices are wrong. If we look at answer choice A, it's saying that decreasing the surface area of the reactants can increase the rate of the rate constant. And that's simply false because if we decrease the surface area, that means less area for collisions to occur and for the reaction to proceed, right? So that means it's going to actually decrease the rate constant. So that's out of the choices. B, create more steric hindrance of my reactants. We can use the arguments of sterics here. If it's more sterically hindered, that means it's harder for the atoms to collide at the same position or orientation, right? So that means it's also going to decrease the rate of the reaction. So we can cross that out. C, decrease the concentration of reactant B. So concentration of reactants is something that is not one of the three factors that affect rate. It's independent of the rate of the reaction. So even if you change the concentration, it's not going to change any of the rate. So that's automatically excluded. And then E, increasing the activation energy, that means you have to put in more energy into the system for the reaction to proceed, right? Which is energetically unfavorable. That's going to decrease the rate of the reaction. And then the correct answer choice D, why is it correct? Because increasing the temperature means we're going to increase the kinetic energy of the molecules and the reaction can proceed faster.
A way I like to think about the temperature is say like my two fists are two different molecules that want to react. If it's cold, they're gonna move like really slow to each other. Whereas if they're fast, they just and they react much faster. So the temperature is how fast they're moving.
That's a good way to put it as well. Yep, increase the temperature. All right. Now that we talked about kinetics and thermodynamics, which is about spontaneity, we're going to, it's very important that you know how to differentiate between these two. So like I said, thermodynamics is the study, it's associated with spontaneity. In other words, it's looking at how likely the reaction is to proceed based on delta G and thermodynamic values such as enthalpy, entropy, and Gibbs free energy. On the other hand, kinetics is purely based on speed. How fast can the reaction occur, right? And what factors that increase the rate of the reaction. All right. So what is this? Yeah, so when we look at an energy diagram like this, to know whether it's kinetically or thermodynamically favorable, we have to look at some values to compare it. When we look at it from a thermodynamic perspective, we're going to look at the delta H or delta G values because that directly tells us the amount of free energy in the system there is, right? And for kinetics, we're going to be looking at the activation energy, or EA simply. This is right here. Because the lower the EA, the faster the reaction proceeds, right? So that directly correlates with the speed of a reaction. So let's do a practice problem here. I'll do the first one with you guys. Is asking us to determine the thermodynamic and kinetic products for the following reaction coordinates. Hint, the products can be thermodynamically favored, kinetically favored, both or neither. So we see that there's two pathways here. Reactants A, B go into products C, D, or E and F. And we're going to determine which one of those two is thermodynamically favorable first. So when we look at thermodynamics, we're going to be looking at delta G, right? So delta G for the blue line here, I'll write it in blue actually, so it's easier. Is this. And then for this red line, the delta G is only around this much, right? And the more delta G or free energy there is, the more thermodynamically favorable it is. So in this case, since the blue line has more free energy, that means it's going to be more thermodynamically favorable. C plus D, thermodynamics. And then from a kinetic perspective, we're looking at the EA, right? The activation energy. So in this case, the blue line has an activation energy of right here, while the red line has an activation energy that is a lot bigger. And for kinetics, the lower the activation energy, the more favored it is kinetically. So in this case, since the blue line has a lower activation energy, that means it's also going to be kinetically favored over products E and F. So in this case, products C and D is going to be thermodynamically and kinetically favored over products E and F. So does my walkthrough make sense? Any part that I need to re-explain? Okay, then I want you guys to do the next example as well. Minutes up. Let's go through this together. Or first off, does anyone want to give an answer? You can talk about the thermodynamics and you can try the kinetics part, okay?
So the C and B were thermally placed, there's a bigger gap between A and B and C and D.
Yeah, right here. That's very true. So yeah, C and D would be thermodynamically favorable. Do you have an answer for the kinetics?
E and F would be better because that's lower activation.
Yep, precisely. It's lower activation energy, so that's the answer. It's pretty simple, right? All right. Okay, so now we're going to look into transition states and intermediates. When we draw energy diagrams, these are important to identify. And transition states are, on the energy diagram, is the highest energy state, where it has the most potential energy. And then intermediates are low energy states, not the lowest, just low energy states. And we can see that on this graph here, for example. This peak here, it has the highest potential energy, right? P energy. Since it's the highest potential energy, that means that's going to be the transition state. And the intermediate, it has a lower potential energy than the transition state, right? So this would be the intermediate. It's not the lowest energy state like this, but it's low enough compared to the peaks. So an easy way to remember this, the transition states are going to be the peaks and the intermediates are going to be the valleys. Okay? You guys can just shout this out since it's pretty easy. Can anyone identify all the transition states and intermediates?
Which one is one? So,
Yeah.
no, is that a transition state or an intermediate?
Transition state.
Well, two,
That would be intermediate.
three?
So is that also just transition state?
Yep.
That's the pattern?
Yeah.
So is it every single one that's pointing downward, the intermediate, and everyone that's pointing upward, the transition state all the time?
Yeah, you can look at it like that.
Yeah, it's like the peaks are transition states and the valleys are intermediates.
Mhm. These values, right? So yeah, that's an easy way to identify these. Okay, this brings us into the Hammond postulate. And basically this Hammond postulate is stating that the transition state or the highest energy state is going to most closely resemble the structure it is closer in energy to. So in this case, we see that this energy state right here is closer to the reactants than the products. There's a huge gap between the potential energy of the transition state and the product, and even less in the reactants. So since the reactants is closer in energy to the transition states, that means the transition state is going to resemble the reactants more. Okay? And FYI, transition states they're not completely reactants or completely products. They're in between. So as we can see here, the transition states, the bromine bond is being cleaved while at the same time the chlorine bond is being formed. That's called a transition state or intermediate. Okay. This we can relate this back to exothermic versus endothermic because if we look at an exothermic process right here, since the transition state is closer to reactants, that means it's going to closely resemble the reactants more so than the products. If we look at the endothermic process, it's closer to the products, so the transition state will look closer to the products. It's basically what it's saying. Okay. Any questions? Nope. All right. Quick practice then. Will this transition state resemble the reactants or products more? Thumbs up for reactants, thumbs down for products. Okay, so we got half actually, 2 reactants and 2 products. Explain yourselves from the people who put thumbs down. Mhm.
I would just say that the transition stage is closer. That's my fault.
Are you good?
It's closer to the reactants.
Mm-hmm. Yep. That's precisely why it's going to be closer to the reactants because the energy difference is less. Yeah. That's basically what the Hammond postulate is. All right. Does that make sense? Reactants. All right. So that covered kinetics. We're going to move on to our third topic. This subtopic is very important. Nucleophiles and electrophiles, because the reactions and mechanisms that we do in organic chemistry usually revolve around nucleophiles and electrophiles. So being able to identify these is very important and knowing how to differentiate them. So first off, let's just give definitions to each of them. Nucleophiles are electron rich and they can donate electrons. So if they can donate electrons, they're very negatively charged. They either have a full negative charge or a lone pair or like a double or a triple bond because they have an excess of electrons they can share. And the name nucleophile literally means nucleus loving or the attraction towards the nucleus. And in this case, they're attracted to the nucleus that has a positive charge or something that's electron deficient. Got it? And then electrophiles are just the opposite of that. They're electron deficient and they can accept electrons. And to accept electrons, that means they're going to have a partial positive charge or a full positive charge because that means they can form another bond. And electrophiles, that means electron loving, their attraction to electrons. That means their love for negatively charged atom species. And that's where they get their names from. Okay. And some of you guys might realize, but these definitions are very similar. Honestly, they're the exact same with Lewis acids and bases, right? So sometimes people use Lewis acids and bases interchangeably with nucleophiles and electrophiles. Okay. So let's go into some examples of nucleophiles and electrophiles. On the nucleophilic side, we have this alkoxide and this bromine ion. We see that they both bear a negative charge, which means they have an excess of electrons, meaning that makes them a nucleophile because they can donate electrons. With this ammonia ion, we can see that there's lone pairs here that can be used for a nucleophilic attack, right? So this makes it also a nucleophile. On the examples of electrophiles, we see that this boron, there's no lone pairs and there's no charge, but this boron can also form another bond, so it can take in more electrons, right? Because boron can form 4 bonds as well. And this carbocation here, self-explanatory, it's a positive charge, so it's going to be electrophilic. Same case with this hydronium ion. They're both positively charged. Any questions so far? Okay. Let's do some practice. I want you guys to identify if the molecules will be a nucleophile or electrophile. And I'll give you guys like 2 minutes for this one. 2 minute pass. Let's do these problems together. So for A, we can tell that this molecule is going to be a electrophile because a nucleophile, an electron-rich species, can come and attack this carbon, which is an electrophilic carbon, because this bromine group is a very good leaving group. And if the bromine group leaves, it's going to bear a positive charge on the carbon. So that's a very electrophilic carbon.
So partial positive charge, even at that form.
Oh, right. A better way to look at it, sorry. The bromine, it's a very electronegative element, right? More so than carbon. So bromine is going to try to hog the electrons from the carbon that's being shared in this bond. So that means the bromine is going to be a partial negative, and this carbon here is going to be a partial positive. And since we have a partial positive here, that means it's an electrophilic carbon. That's a better way to look at it. Yeah. For this instance, we see that this oxygen. What wouldn't? It's a nucleophile though. For this case, oxygen has electrons that around the oxygen atom that can participate in nucleophilic attack, which is why it's a nucleophile. For number C, this can actually be considered both an electrophile and a nucleophile because this oxygen is going to bear a partial negative charge and this carbon is going to bear a partial positive charge. So this is an electrophilic region and this is a nucleophilic region. Oh yeah, we can do resonance here because it's a difference of electronegativity. So you can get something like this. And then we can see here clearly that we have full negative and positive charges, so we can mark these as both electrophile and a nucleophile. Yeah.
A is like that.
A. Um, Bromine is actually a good nucleophile as well. But in this case, the bromine group is seen as a leaving group, so it's not part of the molecule anymore. And we're asking if this molecule itself is going to be a nucleophilic or electrophilic molecule. And there's going to be a partial positive charge on this carbon, which is on the molecule itself. So I think that's why we named this as electrophile instead of a nucleophile. For D, excess of electrons right here, it's double bond. So this makes it a nucleophile. E, it's bearing a positive charge, means it can accept more electrons. So it's electrophile. Any questions?
Obviously,
Nucleophiles are electron rich, right? And one of those forms is a double bond or a triple bond because there's an excess of electrons right here. That means we can use that double bond to do nucleophilic attack and donate it to an electrophilic molecule. Any other questions?
That pi bond is in the ring, I can just assume that's a nucleophile.
Not always, because this branches more into orgo 2 concepts, but if we look at a benzene ring, you can't just use one of those as a electrophile. There's something called what is it? Electrophilic aromatic substitution, and I should not delve too deep into it, but basically, no, not every double bond can be a nucleophile, but in most cases it will.
Just if you see a ring like that with 3 bonds, you probably can't do nucleophile. Just remember that one case. The rest is not really important. Just assume that double bond can.
Gotcha.
Yeah, because I mean, in this case here, this benzene ring, it's conjugated, and it's aromatic ring, and it doesn't want to lose aromaticity by giving away this double bond, so it's kind of unfavorable to use that as a nucleophilic attack, which is why this is usually not a good source of a like nucleophilic uh molecule. But this is more so a concept in Orgo 2 that you'll learn. So you don't need to digest any of the things I just said. Okay.
Thank you.
Yeah, sorry if that confused you. Okay. The answer key. Okay. Another practice, it's asking you to identify the electrophilic sites of each molecule. We can do this one together. Which one do you guys think it is for the first one? So you think A is the electrophilic site?
Oh, wait, I mean, that was the nuclear force. So it would be. um,
Yeah, so you are correct in that A could be like a potential nucleophile, but B is going to be our electrophilic site because it can form potential bonds since it's bearing a partial negative, a partial positive. And that's what it's asking here to find the electrophilic sites.
It's like a partial positive. Is that like a sign that it's electrophilic?
Yep. That's a telltale sign that it's going to be electrophilic. Or if it's bearing a full positive charge, which is probably even more indicative that it's going to be a electrophilic site.
So since you know B is the partial positive, do you have to really look at anything else?
Not really, because none of these bear a charge other than that carbon here. These are all neutral. So you can't do any reactions on those sides. What about this second molecule here? Any thoughts?
C. Negative. I mean, for people letter C up there, so would that be the partial negative?
C would have the partial negative, but is that what an electrophile is? That's more so like a nucleophilic region, right? Electrophilic region would be a partial positive, right? So which of these atoms here, these lettered atoms, are going to bear a partial negative, partial positive charge, sorry.
Would it be the B then?
Yep. Does that make sense? Okay.
There'd be more than one possible.
What was that?
There'd be more than one. So
On this example?
anything.
Yeah, you can have multiple electrophilic sites and nucleophilic sites as well. It's just that we chose this example because there's only one of them. So, yep. All right, so next subtopic is going to be on carbocations. And as the name suggests, it's a carbon cation, meaning it's a carbon that's going to bear a positive charge and it's electron deficient. And carbocations are very important because when we do a lot of reactions and mechanisms, you will form carbocation intermediates. And based on the carbocation, you can make other carbocations where the positive charge on the carbon can shift to other areas. And that can really affect the results of your reaction. So when we talk about carbocations, they can shift to other places based on the stability of them. And there's a trend that follows in determining the stability of a carbocation. And it's listed right here at the bottom. We see that the carbocation with a positive charge and 3 hydrogen groups is going to be a methyl carbocation. If one of the hydrogens is substituted with a alkyl group or an R group, that's going to be a primary carbocation. If there's two of them, that's going to be secondary. If there's three of them, it's going to be a tertiary, right? And to determine stability here, the more alkyl groups that surrounds the positive carbocation, the more stable that carbocation is, okay? So that's why we see here that methyl is the least stable of these carbocations because it's surrounded by hydrogen. And we can use the argument of hyperconjugation to explain the stability of these. Basically, what hyperconjugation is, it's stating that since this carbocation here is surrounded by a lot of alkyl groups, it's going to these alkyl groups will be will donate their electron density towards this carbocation, and it'll stabilize that carbocation more, right? Because electrons are negative and donating more to the positive site will stabilize it. That's why tertiary carbocations are the most stable of these four. Got it? Any questions?
Say that last bit one more time.
Yeah. So
Yeah.
basically, it's saying that if you have a carbocation, the more alkyl groups or carbon chains that surround that positive charge, the more stable it is. And that's because these alkyl chains, they have a lot of electron density that they can donate towards that positive charge, and that those electrons can stabilize the positive charge on the carbon. Whereas in this case, like the methyl carbocation, we see that there's no alkyl chains at all. So this carbon is going to bear a full positive charge without any electron withdrawing groups. That's why it's going to be the least stable.
Gotcha.
All right. Carbocations. Yeah, we just talked about this hyperconjugation, how if there's more alkyl groups around the carbocation, it's going to be more stable. It's basically what it's saying here. Okay. So let's do some practice. We're going to rank the following carbocations in order of increasing stability. So 1 is going to be least stable. And 4 is going to be the most stable. And try to rank these from 1 to 4.
I just ask them like, what's for, what's.
Strap. Let's do this together. This is the first example. What do you guys think the first molecule is? Is it the least stable, most stable, or one of the intermediates?
Stable.
Yep. It'd be the least stable because there's no alkyl chains surrounding that carbocation. So it'd be 1. What about the second example? That would be 3. What about this third one? 2, 4. Yep. That's correct because this is a first degree carbocation, this is a second degree, and this is a third degree. And the more substituted it is, the more stable. Does this example make sense? Okay. Moving on then. Let's answer key. Carbocations, delving into resonance. This is essentially saying if you have a carbocation and it can do resonance, it's going to be more stable than a carbocation that can't do resonance. All right. It's basically kind of like Oreo, where if you can do more resonance, then it's going to be more stable. And we're just applying that logic towards carbocations. So let's do some practice. Rank these carbocations based on increasing stability. And we can see that all 3 of these are a second degree carbocation. So we can't use the degree of saturation to determine whether these carbocations are more stable than the other. So in this case, we're going to have to move on to resonance to determine whether one is more stable than the other. Okay. So in this case, the least stable would be this one right here. Because this one, although it is a secondary carbocation, it can't do any resonance, while the other 2 can, as we will see in a few seconds. So this would be 1, the least stable. And then between these 2, we see that this one right here, it can do a allylic lone pair. A allylic cation, like this. So that is a resonance structure we can do, making it more stable than this one, the third structure. But this first structure can also do resonance with the pi system and a little cation. So that means this is also resonance stabilized. But the main difference between 1 and 2 is that we have a bulkier carbon chain that's coming off of it, right? And since we have a bulkier carbon chain, that means there's more hyperconjugation, meaning like the carbons can donate more electrons to stabilize that positive charge, which is why this first molecule here is going to be most stable, and then this second one is going to be the second most stable. Yeah, that's true. It can do resonance like this, and then it can continue to do the resonance pattern throughout the benzene ring. So there's also more resonance structures you can do with the first one. Does that make sense? Using resonance arguments to determine stability?
It's the thing with like, it has a bigger carbon chain attached to it. Is that, would that always be true, like between the two different ones? If it has a bigger chain, it's probably, more stable.
Uh, Usually, yeah. If it's the same, if we're like comparing two secondary carbocations and one has a more substituted alkyl group than the other, then that will be more stable than the other. So here's the key, 3, 2, 1. All right, I think we already briefly mentioned this, but electron withdrawing and donating groups, pretty self-explanatory based on the name. Electron withdrawing groups is going to take electrons away or withdraw electrons from a carbocation. And just think about it. If we have a carbocation which is already positively charged and it's electron deficient, and we try to take more electrons away from it, what's that going to do? It's going to destabilize it even more, right? Because that carbocation is going to become even more positive. So with electron withdrawing groups, it's going to destabilize the carbocation. On the other hand, with electron donating groups, it's going to donate electrons, right, towards the carbocation. So it's better at stabilizing the carbocation. That's why electron donating groups is going to stabilize the carbocation. Okay? Any questions? All right. Let's do some practice. Let's do this one together as well. So these are all, this is secondary carbon, primary. Fluorine is not an alkyl group. Whatever. We see that we have these carbocations here, right? And we see that this carbocation is bonded to a carbon group. This one's bonded to a fluorine group, and this one's bonded to a bromine group. That's the only difference between these three molecules. And we see that since this one's bonded to a carbon, we already stated that carbons can participate in hyperconjugation and stabilize the positive charge. So that would make it the most stable, which is 3. And then between these two molecules, fluorine and bromine, we see that fluorine is much more electronegative than bromine, right? So fluorine, it's an electron withdrawing group because it wants electrons to fulfill the octet. So since fluorine is more electronegative, that means it's a stronger electron withdrawing group, meaning it's gonna destabilize the carbocation even more. So we would rank it 3, 2, 1, like this. Yep.
So why is the carbon better than the fluorine?
Yeah, so these two groups here are electron withdrawing groups. So that's going to destabilize it. But this carbon atom here, it's a electron donating group. right? And we established that in the previous slide, electron donating groups are going to stabilize the carbocation even more, while electron withdrawing groups are going to destabilize it.
Oh,
So if it's connected to something that's more electronegative than it, it's going to destabilize it. And if it's connected to other carbons, it'll stabilize it.
Any questions? Thumbs up if you guys understand everything so far. Okay, that's good. What the? Why is it 312?
Fluorine is
It's more electronegative, isn't it? Because it's a bigger atom. Oh, is it because
fluorine
bromine,
is that's the most unstable one.
right?
It makes sense that it's one.
Or is it because bromine has more electrons that it can donate? I don't know, even donate.
What did you put?
I put 312 like this, 321.
Oh no, fluorine is more of an electron withdrawing group than bromine. So it destabilizes the cation more.
That's true. Oh, my bad, guys. I put a typo. Fluorine's the most unstable, so it's 312 like this. My bad.
That's because fluorine is more electronegative than bromine, so it's pulling those electrons towards it harder.
Yep, that was my mistake. All right, let's continue on and to our last subtopic, which is mechanisms. So mechanisms, you guys have already done these with acid-base chemistry. Mechanisms is basically the movement of electrons using arrows to show that. And in the case of today's session, we're going to be using nucleophiles and electrophiles to show the mechanisms. So nucleophiles, we said it's electron rich. Electrophiles is electron deficient. So if we see this example on the bottom, we see this ammonia group has a pair of electrons that it can donate, right? So this would be the nucleophile and this would be the electrophile. And yeah, we showed this through these arrow pushing mechanisms. Okay. And for today's session, we'll be focusing on 4 different types of mechanisms. First one, conveniently, is nucleophilic attack, which I've mentioned throughout this session. Nucleophilic attack, as the name suggests, it's when a nucleophile will attack a electrophile. So in this bottom example here, the nucleophile, which is the bromine, is going to attack the electrophile here, which is a positive charge here, and we'll get this product here. And to show that, we show that the arrow is coming off of an electron source, which in this case would be the bromine lone pairs, and then showing it attacking the electrophilic carbon on the electrophile. Okay? One of the simplest mechanisms here. Next one, this is even simpler. This is basically the opposite of a nucleophilic attack. Loss of a leaving group, self-explanatory name. It's when a very good leaving group leaves the main parent chain. So in this example here, our reactants, this bromine's a very good leaving group. So we take this bond here, break it, and then give the electrons to the bromine. And then we'll get these 2 products, right? And if you notice, the products in the loss of leaving groups were the reactants in a nucleophilic attack. Okay? Any questions so far? Nope. All right. Third mechanism, proton transfer. This is also a pretty self-explanatory name. Proton transfer, in this case, the protons are referring to a hydrogen. And Proton transfer is when we take the hydrogen atom of one molecule and then transfer it to another molecule. Thus, we get the name proton transfer. Okay? So we have an example on the bottom here. This carbonyl group has a lone pair, and it's going to use that to stretch out and grab this hydrogen atom. And the electrons that are in this bond right here, it's going to go back to the oxygen atom. So that's how you draw a proton transfer mechanism using arrows. Understood? Questions? Okay. Thumbs up if you guys understand so far. Okay. Last one is going to be rearrangements. As the name suggests, this is when a molecule is literally going to rearrange itself so that it can have a better carbocation. So rearrangement, it's all about getting a better carbocation. So there's two types of rearrangements that we can do. We can have a hydride shift or a methyl shift. And hydride shift is when we use a proton, this hydrogen atom here, and shift it to this carbon, this carbocation, to get this more stable tertiary carbocation. Because if we see here in our reactants, we initially had a secondary carbocation, but if we move this hydrogen to this secondary carbocation, we can move the positive charge to this tertiary carbon, and get a tertiary carbocation. And we know that the more substituted it is, the more stable it is. That's why we can do this hydride shift, and it's favorable. Same case for methyl shift. It's the exact same mechanism, except instead of a hydrogen, it's a methyl group. So we shift the methyl group, and then we get a tertiary carbocation instead. Okay? Any questions with this one? Okay. Do some examples now. So based on the four mechanisms you guys just learned, it shows different mechanisms here, and I want you guys to identify what type of mechanism it is. Okay?
These are the four possible mechanisms.
Yep. So here, for example, I'll do the first one with you guys. We see that this hydrogen is shifted to another part of the molecule so that we can have a more stable carbocation, right? We go from a secondary carbocation to a secondary carbocation, but this carbocation on the products is resonance stabilized, so it's a more stable carbocation. So what group would that be in? That would be in the rearrangement mechanism. And to be more specific, this would be a hydride shift. Okay? I want you guys to, if you know what it is, tell me what B is. For B? Which one are you on? Yeah, take your time. What was it? Leaving group? It would not be a leaving group. What is it?
I was looking at that.
Yeah. You're correct. This would be a nucleophilic attack. I'll just abbreviate it Na. Because we have, in this case, nucleophile would be this water molecule. And we have an electrophilic carbon right here. And we're using the nucleophile to attack the electrophile. So that's literally the definition of a nucleophilic attack. So B would be a nucleophilic attack. What about C? Any guesses for C? That's a good initial guess because the hydrogen is technically leaving the main molecule. But hydrogen, another word for it, it's a proton, right? And this hydrogen is moving from one molecule to another molecule. So what would that be? Yup, precisely. So we can abbreviate that as PT, proton transfer, since we're moving a hydrogen atom from one molecule to another one. What about D?
That'd be rearrangement.
D would not be a rearrangement because we see here, in this case, this OH group on the terminal end of the parent chain, the electrons here are attacking this electrophilic carbon, right? And this OH group, this lone pair is acting as a nucleophile. And we see that the nucleophile is attacking an electrophile and then forming a ring like this. So what would that be?
It'd just be a nucleophilic attack.
Yep, exactly.
If electrons are going towards a positive charge, it's almost always going to be nucleophilic attack. Almost always.
Unless it has to do with a hydrogen like this. Because we see here that we're also using electrons from this water molecule to attack the hydrogen. But in this case, to be more specific, this would be a proton transfer. But proton transfer is technically a nucleophilic attack as well. It's just that Jeske wants you to be specific with these. All right. What about the last one? Yeah, precisely. This would be a leaving group because chlorine is a very good leaving group. So it's just gonna literally leave the molecule and we get to these two products. All right. So that was a good practice. Here's the answer key. Let's do a second one. Jeske will probably ask it this way instead, where he'll give you a multi-step reaction mechanism and then make you identify each step. So let's do this together. So we see that this OH molecule, this hydroxide molecule, is using its electrons to attack a hydrogen. And then this hydrogen is leaving this molecule here. So since the hydrogen is transferring from one molecule to another molecule, what would that be? What was that? Yep, proton transfer. Okay, next step, we see that this deprotonated version, it's using its electrons to attack a electrophilic region. And since this is a negative charge, that means it's going to be a nucleophile. So what would this be? Using a nucleophile to attack an electrophile. Nucleophilic attack, right? Oops. This would be a nucleophilic attack. And then last one here, we see we're using this electron from the oxygen to make a double bond. And then this OR group is leaving this ether group. It's literally leaving the molecule. So what would it be? Leaving group, right? So that would be the answer. Do these make sense? Any questions?
What was the last one? The leaving.
Yeah, so this is a leaving group because we have this OR group that's leaving the molecule itself. But in this case, to show the mechanism, they're using two arrows because we can't just show this arrow to show the ether group leaving. We have to use the lone pairs here to make a carbonyl again, and then expel this OR group again, this ether group. So that's why it's a leaving group.
Is it showing above the equilibrium? The RO.
Oh,
That's what's leaving.
yeah.
It's like a byproduct, but like next to the product.
That's why it's saying, yeah, whatever. Yeah, that's the byproduct. Yeah. Last practice problem, and we'll be finished for today. identify if the carbocation is likely to rearrange. So with rearrangement, we said that we'll do carbocation rearrangement if it produces a more stable carbocation, right? So look at the carbocation initially and see if moving that carbocation will result in a more stable carbocation. So for example, I'll do the first one with you guys. We see that this is initially a secondary carbocation, but on this carbon here, we have a hydrogen. So what we can do here is we can do a hydride shift, and then we would get this molecule. The positive charge would now be on this carbon instead of the carbon before. So now this carbon, this positive charge is on a tertiary carbon. And we know that a tertiary carbocation is more stable than a secondary, right? So in this case, a carbocation rearrangement is likely to occur. Does that make sense? Yeah.
So, June, you moved the hydrogen
Mm-hmm.
onto where the charge was before.
Yeah. That's called a hydride shift. And we did that because if we do that, it'll result in a carbocation that's tertiary. And tertiary is more stable than secondary, right? That's why we can do rearrangement. Next one. So this one's yes, we can do carbocation rearrangement. For B, does anyone have a guess on if no rearrangement? You guys are correct. This one, it's already a tertiary carbocation, and the only way it can do another, if the only way it can do a rearrangement is if you can get a carbocation, the tertiary carbocation that can do resonance. But in this case, even if we move the partial charge, the positive charge to here, it's still a tertiary carbocation. So there's no use in doing a rearrangement at this point. That's why, no, it is not likely to rearrange. Okay? What about the next one? C. So what's your answer?
Would be on someone.
That's a good point. But remember, rearrangement, there's two types. You can do a hydride shift or a methyl shift. So in this case, what could you do to, if you can do rearrangement?
Would I do a mental shift?
Yep, that's correct. So even though we have a tertiary carbocation here, we can do a methyl shift and get this structure. And we see that this positive charge is now still a tertiary carbocation, but it's in the presence of a double bond. And this double bond can do an allylic lone pair like this. And since it's resonance stabilized, this tertiary carbocation here is more stable than this one. So as a result, rearrangement is likely to occur. Okay? Last example. Wants to take a guess with this one? No? Yeah. You're correct, because I mean, even if you do any hydride shifts, there's nothing you can do. Like, it wouldn't change anything, because any rearrangement you do would result in a secondary carbocation. So here's the answer key, and that'll conclude today's session. Yep.
So if the charge can move closer to being able to do resonance, that make it better.
Yes. But the first thing you always look for is if it's primary, secondary, tertiary. And if it's the same, if it's like two tertiary carbocations, then you move on to resonance to determine if it's more stable or not. It's not always as if it can do resonance, only if the carbocations have the same degree of saturation. Okay? Yeah, that's it.
No feedback slide.
No feedback slide. Um, and just go back to like we can scan this QR code for feedback.